Hello everybody, and thanks for opening this pre-recorded talk. My name is Tomas and I'm going to report on our recent work on altermagnetism, in which we delimited this third magnetic class formulated by spin group theory. And before I begin, let me point out the leading role of the first author on this work, Libor Smejkal. We're all perfectly familiar with the first class of magnetic materials, ferromagnets, which are crystals containing magnetic atoms whose moments are ordered in parallel. And as a result of this exchange polarized magnetic moments, we also get exchange split electronic structure into the majority and the minority bands. And the spin splitting of the electronic structure has very favorable consequences for magnetic recording, or spintronics in particular, where we use these spin polarized currents, which are due to the non-relativistic spin polarized band structure. And these spin currents can be used for reading magnetic information by phenomena like giant magnetoresistance or tunneling magnetoresistance. And the same non-relativistic spin currents can be also used to write the information in these spintronic devices by spin transfer torque. Now, the second class of magnets that we are quite familiar with are antiferromagnets, which are composed of at least two distinct magnetic sublattices, and in the simplest form with the moments which are anti-parallel. And because of the fully compensated magnetic moments, these conventional antiferromagnets have spin-degenerate non-relativistic bands. And this directly implies that we cannot use the phenomena known from ferromagnetic spintronics, like giant magnetoresistance or spin transfer torque, for reading and writing information in antiferromagnetic devices. So this was the reason why the initial efforts to use antiferromagnets in spintronics was based on reading and writing phenomena which were relativistic. In particular, for readout, it was this relativistic and isotropic magnetoresistance, and for writing, the relativistic spin orbit torque switching. And indeed, with these relativistic phenomena, it was possible to demonstrate reversible polarity-dependent electrical switching of large antiferromagnetic domains, like for example in this X-ray imaging experiment, where the current pulses with the opposite polarities are switching the Néel vector between these two orthogonal directions. And apart from imaging, we can use this electrical and isotropic magnetoresistance to the electrical readout, and then with the electrical writing and readout, we can demonstrate implementing experimental antiferromagnetic digital bits in these simple digital printed circuit boards and operate them, for example, from a personal computer. And these bits can represent logic zeros and ones corresponding to these, for example, these two orthogonal direction of the Néel vector. While this is purely relativistic, you can also do non-relativistic spintronics in antiferromagnets. However, the phenomena that are behind this for reading and writing are completely different from the non-relativistic ferromagnetic spintronics. In particular, what you can do in antiferromagnets is by sending electrical pulses of different amplitudes, you can control the type of antiferromagnetic texture you have in your memory device, all the way from micron scale domains to nanosize textures in your system. And with this type of switching, you can also achieve large non-relativistic changes of the resistivity of this device, which corresponds to the different types of nanotexture that you have written in the device. With this non-relativistic concept, you can realize not only these digital memory experimental devices with bias stable switching, but you can realize many intermediate states which can have also highly reproducible, time-dependent switching and relaxation characteristics. So these devices may be favorable for designing not the conventional digital memories, but analog memories mimicking components of the artificial neural networks. With this nano fragmentation switching mechanism, one can replace the electrical pulses also with optical pulses and demonstrate switching scaled down to the ultimate single femtosecond laser pulse. And finally, because these are antiferromagnetic devices, they are, unlike ferromagnets, highly insensitive to magnetic field perturbations. And in these particular switching concepts, it's been demonstrated that even 60 Tesla field is not disturbing the functionality of such an antiferromagnetic device. So we can at least experimentally demonstrate spintronics based on antiferromagnets, but if you've seen, the principles of the operations are completely different from the conventional commercial ferromagnetic spintronic devices. They are either based on fully relativistic operation, or if non-relativistic, then we are not controlling the net orientation of the magnetic order vector, but instead what we are controlling is the type of the texture that is written in the device. Well, remarkably, over the past couple of years mostly, several groups all around the world, including our groups, have reported unexpected anomalies in some collinear antiferromagnets, which hint towards the possibility of realizing the conventional spintronic functionalities that we're familiar with from ferromagnetic spintronics. In particular, there were mostly theoretical reports of features which are analogous to ferromagnets, like, for example, large non-relativistic spin splitting in the band structure, or large anomalous Hall effect, large predictions of large non-relativistic spin polarized currents, giant magnetoresistance, etc. The purpose of this talk is to look at these recent reports not as anomalies in some unconventional collinear antiferromagnets, but instead show that we can look at this as a regular characteristics, but of a distinct magnetic class, and the magnetic class we will call altermagnets. Now, what is the distinction from the conventional two magnetic classes? The difference is that the states are still fully compensated in the non-relativistic limit, so there is no net magnetization. However, when we look into the band structure, there is spin splitting or spin polarization. Now, I will, in the next slides, I will delimit these three classes using the formal spin group theory. And it's not just an exercise for itself, a mathematical exercise, but it's important for bookkeeping. We will make sure that while discovering this third class, we're not missing a fourth or fifth class. It's actually a complete classification of non-relativistic collinear magnets. And second, having a formal group symmetry theory will guide us towards the most favorable candidate materials where we can observe this magnetic type of magnetic order. But before going to this formal theory, let me just briefly outline the main result. So what is the distinction between the conventional antiferromagnets with spin degenerate bands and these altermagnets with spin split bands? In both cases, the magnetization, the non-relativistic magnetization, precisely vanishes. And this can only happen if the crystal is composed of at least two crystallographic sublattices which carry opposite magnetic moments and which are connected by some crystal symmetry operation. If that is the case, then the magnitudes of the two moments are forced to be equivalent, and if they are antiparallel, then the net magnetization vanishes. Now in crystallography we have basically three types of crystal symmetry operations. It's either a translation or inversion or rotation. So when the two sublattices are connected by translation or inversion, we will show that the resulting bands are spin degenerate, so we have the conventional antiferromagnetism. However, where the symmetry operation connecting these two opposite magnetic sublattices is or contains rotation, in this case we will again get zero net magnetization. However, the spin polarization is now allowed symmetry. So let me go to the formal description of these three types of magnets by the spin symmetry groups. As I said, we want to describe physics, which is non-relativistic, and we're going to limit the discussion today to collinear antiferromagnets. So the non-relativistic physics that we want to describe implies that we need to consider symmetry operations in the crystal space and in the spin space which are decoupled, because we do not want to look at phenomena of relativistic spin-orbit coupling which couples these two spaces. And second, since we're limiting ourselves to collinear magnets, the only symmetry operation in the spin space that we need to consider is just a spin reversal or 180-degree spin rotation operation. The observable that we want to describe by this spin group theory is band structure, momentum and spin-dependent band structure. So this is one of the fundamental observables in any system. And so let's take a look what type of crystal symmetry operations we need to consider when we want to classify these band structures. So we do not have to consider translation when developing the spin groups, because energy bands, momentum and spin-dependent energy bands are invariant under the translation operation. So instead of considering all 232 crystal space groups, we can just limit the classification to the 32 crystal point groups. Those are the groups which do not contain the translation element, symmetry element. Now, our bands are not only translation invariant, but they are also inversion invariant or inversion symmetric. The reason for this is that there is an equivalent symmetry operation to inversion, which is a combination of time reversal and spin rotation. So these two operations, when they are acting on the momentum and spin-dependent band structure, they have the same result. But simultaneously, the combination of time reversal and spin rotation is a symmetry of a collinear crystal, because when I time reverse the spins, I flip them, and when I do spin rotation, I flip them back. So these two symmetry operations, the time reversal and spin rotation and inversion, they act the same way on the band structure. This one is a symmetry of the crystal, and that means that also our bands have to be inversion symmetric. And that allows me to limit all the considerations just to these 11 inversion symmetric crystal point groups. And now I'm going to construct the spin point groups to describe my magnetic band structure, and this I will do by combining these crystal symmetry operations with this independent 180-degree spin rotation. And remarkably, there are only three ways how I can do such a combination in a way that what I will end up with is a group. And one way is that the spin group is going to be equivalent to the crystallographic group. That means there will be no spin rotation element present in this group. And so it means that this first class of spin groups would be identical to the crystallographic groups, and we will have again 11 spin groups of this class 1. The other possibility is that we will get a spin group in which the spin rotation is a symmetry. And that also means that every element from the crystal point group, which is a symmetry, will have a corresponding element which is the same crystal symmetry operation, but now combined with the spin rotation. And this is also going to be a symmetry in our system. This is equivalent to saying that our system has this spin rotation symmetry. Now, the only third possibility, a distinct possibility how to construct a spin group, is by halving the crystallographic group into two parts. The first half is going to be without the spin rotation operation, and the second half will be combined with the spin rotation. So this is the third possibility here, and when we count all different spin groups constructed with this mathematical prescription, we will see that there is 10 of them. So we have now constructed 3 different types of spin groups, which are comparably abundant in terms of how many different group elements I have in one of these classes. So the first 2 have 11 elements and the third has 10 elements. And now I can make the step towards our magnetic classes and associate these 3 different spin group types with the 3 different magnetic classes. So ferromagnets are described by the first group, and this is because this group does not contain any spin rotation element. So in such a magnetic crystal, it means that there is no transposing symmetry which will transpose one magnetic sublattice onto another sublattice with the opposite magnetic moment. So if I don't have such a transposing symmetry, then by symmetry I have magnetization, non-zero magnetization is allowed, and that corresponds to a ferromagnet. Now, when I look at my band structure, because all my symmetries are such that they do not contain this spin rotation operation, for any k vector and spin, when I look at the eigenenergy of the reverse spin, it's in principle different because there is no symmetry operation that would connect eigenstates with opposite spins. So my band structure is in principle spin polarized. On the other hand, I have the type 2 spin group, and this type 2 spin group is the one which has the RS symmetry. This one corresponds to magnets which do have transposing symmetry, but only 2 possibilities. The transposing symmetries are either translation and then combined with the spin rotation, or inversion and then combined with the spin rotation. And why is this equivalent to having an RS symmetry? It's because a combination of translation and spin rotation and translation symmetry, and we've shown before that our bands are translation invariant, implies that the bands are also invariant under the spin rotation. And the same applies to inversion. So if my bands are invariant under spin rotation, because my symmetry group has spin rotation as a symmetry element, I can take a look what the RS symmetry operation does to my momentum and spin dependent bands. It just flips the spin and leaves the momentum the same. But since this is a symmetry, that means these 2 eigenstates have to have the same energy. So I have spin degeneracy at every momentum, and this is conventional antiferromagnet. Now, in our altermagnets, this is the 3rd scenario. I do not have the RS symmetry. I have an RS symmetry combined with rotation here. So when I apply the symmetry operation combining spin rotation and a crystal rotation, on my energy eigenstate here. I get the opposite spin eigenstate, but I have that eigenstate with the same energy but at a different momentum. And that implies now that in general, whenever this crystal rotation operation moves momentum into a momentum which is different, then at these momenta spin polarization is allowed. So I can now take a look at all the 10 spin symmetry groups that we've delimited here, and based on the symmetry of the group, I can look what is the basic topology of the spin momentum coupling. So the basic topology I can derive from how many times the spin rotates when I go around a closed loop around the gamma point here. So I see that for these first 3 spin point groups, the spin flips once and the second time. So when I go around the whole loop, I have winding number 2. Then I have this type of spin point group where the spin flips 4 times, so I have a winding number 4, and I can also have 6 times flip. And these are the types in which when I go in, so this was rotating in the kx, ky plane, and when I look at what happens with the spin by going through the kz axis, the spin remains the same. So these are 2D or planar-like spin momentum couplings. But I can also have these bulk spin momentum couplings, and again with a total winding number 2, 4, or 6. Now here is the time to compare this spin momentum coupling in these non-relativistic altermagnets with the spin momentum coupling we might be more familiar with, and that is resulting from the breaking of the inversion symmetry and adding relativistic spin orbit coupling. So the typical example is the non-magnetic relativistic Rajpa spin orbit coupling, and what you see here is that the band structure is inversion asymmetric. When we go from one momentum to the opposite, also the spin flips. So this is distinct from the spin-momentum coupling in our altermagnets, which are inversion symmetric. Now in the relativistic physics, you have the typical spin texture, so the spin quantization axis changes when you change the momentum, while in altermagnets they are non-relativistic and you can define a single quantization axis for all momentum. And in this Rajba system, you see that you have an odd winding number. The spin rotates only once around the loop, while here in altermagnets we have always even winding numbers. So this was about the basic topology, and now let me move on to spectroscopy. So the question is, what is causing the spin splitting here in the band structure, and how we can control it? So in ferromagnets, we know that the splitting is because of the exchange interaction. In these conventional antiferromagnets with spin-degenerate bands, we also see splitting of the bands by the exchange interaction, but there is no spin splitting. And the reason is that the lower energy state here is a mixture of the favored spin orientations from both spin sublattice, so upspin for the green and downspin for the purple sublattice, and then the higher energy state is a mixture of the, let's say, disfavored spin, so it's the higher energy spin up state from the purple sublattice and the higher energy spin down state for the green one. Now in these altermagnets, you also see that there is this exchange, a splitting of the bands, but what is governing the spin splitting at the given momentum is a different mechanism. So let's take a look what this mechanism is. So what we see is we look at the specific eigenstate at a given momentum k, and now when we apply our transposing symmetry operation, which is a rotation, it actually changes the momentum to a different momentum with an opposite spin and the same energy. Now when we are looking back, what happens for this opposite spin sublattice state when we move back to the original momentum? And what we see here is that the energy is different. So what it means is that the local environment, the local crystal environment of a given sublattice has to be anisotropic. And when the local environment is anisotropic, then when I go with the state belonging to the same sublattice from one momentum to here, for example, orthogonal momentum, I see that the energies are different. So it's the local anisotropy which is critical for having this spin splitting. So we see that the spin splitting is governed by the crystal anisotropy field of the crystal environment of a given magnetic sublattice. But on top of this, these anisotropic crystal environments have to have these anisotropy axes mutually tilted between the two sublattices, because only then the two sublattices are connected by a rotation symmetry. If the two anisotropy axes were not tilted mutually, then I can have the translation or inversion transposing symmetry, and I will get back degenerate band. So here is a specific materials realization of altermagnetism is potassium ruthenium oxide. And what you see is exactly exactly the properties required for a large spin splitting. We have locally anisotropic crystal environments of these ruthenium atoms surrounded by the oxygens, and so it's a strongly uniaxially distorted local environment. And when we look what is the symmetry operation that connects the opposite spin sublattices, it's this 90-degree rotation. So these are the requirements for having this large momentum dependent spin splitting, and these are the ab initio bands, and as you see, they perfectly correspond to our model consideration. Now we've seen from the symmetry analysis that this class of altermagnets can be quite abundant, and indeed I'll show you two more examples. One is an insulating, representative of insulating altermagnets, copper fluoride, which also have this rotation symmetry connecting the opposite spin sublattices, and it has this spin dependent or momentum dependent spin splitting. And another example, maybe surprising, is that the altermagnetic order can also form in the parent cuprate materials. The example is this lanthanum copper oxide here, which also has this locally anisotropic oxygen environment of the magnetically ordered copper atoms, and these anisotropy axes are mutually tilted. And as a result, this parent cuprate will have an altermagnetic order with this winding number 2, or if you want, in orbital harmonic symmetry, it will have a D-wave symmetry of the spin momentum coupling, and that is reminiscent of the D-wave symmetry of the superconducting band gap in this cuprate superconductor. And so finally, let me show you an example of a spintronic effects that we can get in these altermagnets with the spin polarized band structure. So the first effect is a non-relativistic spin current. So here you see an example of this anisotropic spin split Fermi surfaces, where red corresponds to one spin orientation and blue to the opposite. And now imagine that you apply electrical bias along one direction, and because of this anisotropic Fermi surfaces, you will have majority current carried by spin up electrons and minority current by spin down electrons. So you have spin polarized current in a system which is zero magnetization and equilibrium. And so this is then reminiscent of ferromagnets. However, now when you apply the electrical bias in the orthogonal direction, you will also get spin polarized current, but now the spin polarization will be reversed. So you can reverse the spin polarization of the current by reorienting the applied bias. So this is certainly something which is not observed in ferromagnets. And another unique feature is that when you apply this bias along this diagonal direction, your longitudinal current will be unpolarized. So this will be reminiscent of antiferromagnets. However, you will also generate a transverse now zero electrical current, but pure spin current in the transverse direction. Now, this transverse current is not like a spin Hall effect because it's purely non-relativistic, and because of this, the charge spin conversion ratio can be very large. In this ruthenium dioxide altermagnet, it's around 30%. And finally, since you can generate spin polarized currents in these altermagnets, you can think of constructing stacks. And when the Néel vector is anti-parallel in these systems, you will generate a high resistive state. And when they are parallel, you can generate a low resistance state, exactly in analogy to ferromagnets. And again, ab initio calculations in this ruthenium dioxide suggest that these giant or tunneling magnetoresistance can be very high. So this brings me to the conclusion. We have formally delimited using non-relativistic collinear spin group theory 3 distinct non-relativistic magnetism classes of ferromagnets, antiferromagnets, and altermagnets. All the conventional spintronics is based on this non-relativistic ferromagnetic order. We've seen that there are intriguing new functionalities and characteristics of antiferromagnetic spintronic devices, even when they are constructed based on these conventional spin unpolarized antiferromagnets. And now what I try to convince you that there might be a third class which can be comparably abundant, where the favorable features of ferromagnetic and conventional antiferromagnetic spintronics can be combined, but it might also open connections to very distinct fields from spintronics. An example is superconductivity. So thank you very much for your attention.